In this recording, we will be talking about regression models. In regression based forecasting, we pick predictors that describe what drives the series. Is it time for a trend, month, for seasonality, or maybe some other external variables like advertising spend? Once we trained the model as we used to do before, we can forecast by inserting future values of those predictors into the equation. The good part about the regression model is that it has multiple forms. So we can have only model the trend, we model the seasonality alone, the trend alone. The trend, we have multiple trends, types of trends. We have linear, we have exponential, we have polynomial. And for the seasonality, we can adapt it to be additive or multiplicative. And then we can do easily the forecasting process as we used to do, like partitioning the data into two parts, training validation, build the model on the training data. After that, forecast for the validation and check the accuracy measures, and we will be adding some more measures. We will be looking at the residuals. Anyway, so this is kind of the linear regression. So the first part we will be talking about is modeling with linear trend, just a trend. So suppose that you have a trend in your data, and this data looks linearly trending upward or downward. Then we can use regression. So that gives you the overall pattern that runs through the whole time series. And it takes multiple forms. The trend can be linear. If it's linear, that means it rises or falls at a steady pace. It can be exponential trend. If it's exponential trend, it captures multiplicative growth or decay. And if the pattern has that curvy shape, it's like bending or levels off or whatever, then we are talking about polynomial. Polynomial starts from second degree, third degree, and so on. So the point is to build in this trend. The point is to build a regression equation that carries this long-term tendency forward when we forecast. So in our example, for example, in Amtrak ridership, we have the month as our time series, as our time, and we have the ridership. So the response variable or the output is the ridership. We would like to get information about the ridership, and our predictor is going to be the time for the trend. So we're going to give the first time point, number one, second time point, number two, and so on. So this is going to be my predictor. So this is going to be my predictor. This is going to be my response or output variable. So the equation is going to be something like this. Because it's a linear trend, yt is going to be beta naught plus beta 1t plus the noise, which is the epsilon t. Okay. And b naught is the level. We are modeling the level here. We are modeling the trend here. And this is the noise. And if you look at what we have right now, we know that in Amtrak ridership that the behavior of the time series is not linear, but this is just for introduction or illustration that, hey, let's see how the linear model is going to do. So this is how the model does for the validation test, which is it's not close to the behavior of the validation. Remember, we train the data, we train the model on the training data, then we tested this on the validation. But if you look at the behavior, it's straight line, and it doesn't reflect the real trend of the Amtrak. We know the trend is kind of a curvy, it takes curvy shape approximately from here. It's curvy. It's like a U-shaped thing, right? A regression model, when we do a regression model on the trend here, when we model with a trend, we do not focus or look at the significance of the p-value or the betas, because the model is not ready. I mean, we should have first deseasonalize this one, because we have seasonalities here. So when you give me a trend, that means these betas and p-values are not reliable. So we would not look at them. We just look at the overall performance. So it's not correct to look at these values in the current situation. The good part is If you do, if you build a model, first of all, you have to look at the plots. You look at the plots, you forecast the errors before concluding whether the linear model is the trend is appropriate or no. Maybe we want to try to model the trend with an exponential trend. The exponential trend means that we have a multiplicative increase or decrease of the series over the time. And this is not really the case over here. It's not multiplicative 100%. In some cases, yes, in some cases, no. But what is the equation that we use is yt equals c times exponential beta 1 plus epsilon. If you take the log to both sides, it's going to be like this. It's going to be a linear trend. It's going to be a linear trend, which is log yt equals beta naught plus beta 1 t plus epsilon t. So the point is, if you want to compare this trend, exponential trend, with the linear trend, we have to make sure that we compare it correctly, because this is log. This is going to be the value for log yt. The one before is yt. So when you do the comparison, make sure that you have the same scale. The third trend, if you just model the trend for the Amitrack, if you look at it, this is the trend, and it captures most of the trend. So it is most of the trend. Okay, we have something here. It's not 100% going up. It's you for the training, for the validation a bit, it goes up. Then we have something should be like a little bit down. But this captures overall the trend. And the polynomial in this case is t squared. I mean, it's the parabola. We do not. Someone's going to tell me why don't we go to third degree or fourth degree, etc. If you do more than this, you are going to probably to have something called overfitting. Overfitting, when you are fitting the past values perfectly. Okay, and this is going to be failing miserably when new data gets in. So when you try to check the new data on the model that you have built, it's going to do really poor. So that's why we don't look at the overfitting thing. We are not very careful. We are not interested in making this exactly looking the same exact trend, but overall it models well. So if you look at the equation that we have yt beta naught plus beta 1t plus beta 2 t squared plus epsilon. So this is the trend. T is the trend. And yeah, so in regression, we can do this with trend, and we can model with seasonality as well. We can model with seasonality. We know that what is seasonality is a systematic pattern that repeats at fixed intervals, like months, quarters, days, hours, etc. Some seasons always have higher or lower values. In Amitrack data, the summer months consistently show higher ridership, and we have seen this multiple times. So the first step is we have to first to recognize this pattern visually in a time series, because it signals that a model ignoring seasonality will systematically over or under predict in certain months. So you have to see it first. To incorporate seasonality into a regression model, first we start by adding categorical variable, which is in this case, in our example, it's a month. Why? To mark each observation season. So we just add a categorical variable. Then we change that variable into dummy variables. So if you have m seasons, we are going to have m minus 1 dummy variables. So each one's going to take one out of two values, either 1 or 0. So if the observation belongs to the season, it's going to take 1. If not, it's going to be 0. And one of the seasons is going to be like the reference point. If all of the dummy takes values of zeros, then we will be having the reference season. Yeah, example. Let's look at example. In Amtrak, we have 12 months. M is a 12 months the width, right? And the seasonality is monthly, and it repeats every 12 months. So we have m is 12. So we are going to have m minus 1, which is 11 dummy variables. So we are going to build a model with seasonality only, no trend, no t. So it's going to be the equation like this: yt equals beta naught plus beta 2 m2 up to beta 12 m12. So these m's, this is for the second month. M3 is the third month. This is month 12. So if M1, if M2 is 1, others they're going to be zeros. Or if this is 1, that means we're talking about month 2. If all of them are zeros, then we're talking about month 1, the one that we have not included here. And if you have additive seasonality, as in this case, we capture the additive difference between months, and we talked about this. For example, if August's coefficient is 396 riders, that means we have plus 396 passengers versus January compared to January. So if you look at this model that we have here, we just modeled with seasonality for our ridership example, and it captures the seasonality well, good in both training and validation. However, it doesn't capture the trend, so it's like a straight constant line. It's not going down or up. It's not showing any trend. Why is that? Because we have just model with seasonality only. We did not look at the trend in this case. So the residual, if you look at the residual, it's going to show the U-shaped trend. So the model technically over predicts the middle years and under predicts the start and the end, because the residual is not random. We are expecting the residual plot to be random. So if the residual is not random, if it has a behavior, if it has a pattern, so we need to think about adding something. In this case, we think about adding a trend part because we know that it's not doing well in the trend. Again, what is the residual? Is the difference, just the simple difference between YT, FT, the actual value and the predicted or forecasted value. So YT minus FT. YT minus below zero. Below zero, that means you are over predicting. Above zero, that means we are under predicting, right? So because the residual has a pattern, it doesn't show any random behavior, then we have to think about adding another term for the seasonality, which is the trend. And it makes sense because we know that the Amtrak already has a trend. And sometimes the seasonality is multiplicative. So like the seasonal effects are proportional, not additive. Like sales rise 15% every December rather than by a fixed value, right? In this case, we are going to have multiplicative seasonality, right? If we have multiplicative seasonality, we think about applying the log y, same regression structure, but we use log y as the dependent variable. In this setup, the coefficient is going to translate into percentage differences between seasons instead of absolute values or ones. As we said, a model with seasonality is not enough. Model with a trend is not enough for our example. Some examples you are. Some example you have only trend. Some other examples you have only seasonality. So you just build and you have to look at to the time series before, right? In this case, in our example, we have to think about model with a trend and seasonality. So we're going to create a model that captures both trend and seasonality. And because we know Amtrak, the behavior of Amtrak is curvy, we know that the trend part that we are going to add is going to be the quadratic form, which is beta naught plus beta 1 plus t plus beta 2 plus t squared. And we know that the seasonality, we have season every 12 months. It repeats, right, every 12 months. Then we're going to add the 11 dummy variables, takes values zeros, ones. And remember that we just eliminate the reference month, which is the first month, January, to represent February, and this is December. And now if you look at the pattern, now we captured technically both parts, the seasonality, most of the seasonality and most of the trend for the training. When we apply this to the validation, it seems that we are over predicting, because if you look at the residual plot for the training data, we have a random behavior. This is approximately random, because you're going to look at around the zero, how the plot look like. Is it curvy? Is it taking some shape? No, it doesn't. Any pattern? No. It's random here. However, it's decreasing here. It's decreasing. So the model is well fitted to the past pattern, the training, but fails to keep up with the new level of the series in the validation window. So, what does it mean? It means that the trend probably has changed. So, either flatten or reverse, and we can see it. As we mentioned before, the trend here, it's not behaving like this. It's not going up like that. It's going down here a little bit. So we are not saying that the model is wrong. The model is very good so far, but we can still adjust and add some other techniques to that one, or maybe we can use other models or other method that will capture these issues, right? Because this is, look at the validation, it's below zero. Below zero it's negative, so we are over predicting the and it's clear from here. It's clear from here, we can see it, because this is yt minus ft. Remember, that means ft is greater than yt because it's less than zero, right? So what we do finally, after getting different regression models and choosing the model that to be used for forecasting, we refit the chosen regression model to the combined training and validation periods. Then the model can be used to generate case step ahead of forecasts. So this is the way that we started with in this time series classes, and this is the way that we are going to keep doing most of the time. Thank you.